right, welcome back everybody. We're still going over our chapter 26 lecture here, which has to do with DC circuits. And the last topic in this lecture, since we just covered Kirchhoff's laws, is something called RC circuits. So let's get into RC circuits, what this is all about. So the big picture is, when we've used Kirchhoff's rules in the past to figure out some unknown currents in a DC circuit, up until this point, we've only been looking at problems where you have like a bunch of resistors and maybe a bunch of different batteries connected in some way. Now, that can get kind of complicated because there might be a lot of different currents to solve for, but fundamentally, we're getting equations that are what we call algebraic. Okay, so let's say I apply the loop rule or the junction rule to a circuit. I'm getting some kind of algebraic equation. All I need to do to solve the system of equations is just use algebra. And again, it can get kind of tedious, but it's all algebra. And this means when we solve an algebraic equation for, let's say, an unknown current, we're just going to get a number. Okay, so for instance, if I solve for I1 or I2 or I3, I'm getting just some constant number, which means these currents aren't changing over time, right? I1, half an amp. I2, 0.2 amps, for instance. These are just constant currents that don't change over time. When we move on to RC circuits, now what we're talking about are circuits with batteries, resistors, and capacitors in some combination. And fundamentally, when we use Kirchhoff's rules to figure out what's going on in a circuit like this, the equations look different. They're not algebraic anymore. Now they're what we call differential equations. So a differential equation is just an equation that involves derivatives of some kind of function. And fundamentally, if we want to solve a differential equation, it's going to require calculus. Okay, there's not a way to do it algebraically. And another thing that makes a differential equation different from an algebraic equation is that, again, when you solve an algebraic equation, you just get some number for your solution. When you solve a differential equation, what you get is a function. For instance, the current will be a function of time. Rather than some constant value, it's something that changes over time. So this is a little bit different than what we've seen before. And so I'm going to start you off with some questions for the class to get you kind of thinking about what's going on in an RC circuit and how currents and therefore charges on the capacitor are changing over time. All right, so this one says, consider the circuit shown below, where epsilon, this battery, has an EMF of 10 volts. Both resistors that you see here have a resistance of 10 ohms, and then the capacitor has a capacitance of 10 microfarads. So what we have here is a switch, and right now the switch is open, meaning no current is going to flow in any direction. But what we can do is flip the switch to either point A or point B. Now what happens when I flip the switch to point A? What happens is I connect the battery to the capacitor, which means I can charge it. Okay? On the other hand, if I flip it to point B, I'm connecting the capacitor to this resistor, which means I can discharge it. Okay, so for now, let's think about throwing the switch to position A, which means we're charging the capacitor. A couple questions here. What is the current through the resistor, that would be this one right here, and the charge on the capacitor immediately after the switch is thrown? So immediately when this makes contact with point A, what is the value of Q, and what is the value of I for this circuit? So let's work it out. So the situation kind of looks like this. We've got the battery with an EMF, epsilon. We've got a resistor up here, and we've completed the circuit by connecting this to the capacitor. Now the other side of the circuit on the right is actually not connected, so we don't have to worry about that. We just worry about this loop right here. So we have a resistor R and a capacitor C. So the first question is, okay, let's call it t equals 0. That's immediately after the switch is closed. What do we know about the charge on the plates of the capacitor and the currents? Well, the charge question is easy. Q is just equal to 0. Why is that? Well, we don't start off with any charge on the capacitor plates. And it takes time for charge to move through the circuit and actually get onto the capacitor plates. So if no time has passed, then we don't have any charge building up because it fundamentally is going to take some amount of time for the charge to get there. So no time has passed, no charge. Okay, so Q is 0 since no time has passed. All right, so let's just put 0 charge on the plates, like this. Now let's think about the current. Okay, so this is the positive and negative terminal of my battery, and I know which way current is going to tend to flow. In this case, it's going to flow clockwise. And I don't want to say the current is 0, right? And there's a reason for this. Let's take the loop rule for this circuit that I drew. And how about we start down here and then make our way around the circuit going clockwise. So, okay, I've got epsilon, and I have a positive sign on that because I'm going from the negative to the positive terminal of the battery. Then I'm going across the resistor in the same direction that the current is flowing, so I have minus I times R. And then I'm going across the capacitor. So technically this would be the positive plate once we start to have charge there, and this would be the negative plate. So if I'm going from positive to negative, I would have a negative voltage, Q over C. But here's the thing, there's no charge on those plates yet, so we can actually set that last term equal to 0. Okay, so set Q to 0 because no time has passed and we don't even have any charge building up yet. So we get something kind of simple, which is epsilon is equal to I times R. So the current is epsilon divided by R, and these were both exactly equal to 10. So we have 10 volts over 10 ohms, which is a volt per amp. So 1 amp of current. Okay? So immediately when we close the switch, we have an amp of current, and we don't have any charge on the plates yet. But of course, if we wait some more time, if you think about it, we will have charge on the plates because that's what this current is doing. It's carrying charge to the plates of the capacitor. So things are kind of dynamic and changing. This is not just a constant current. This is the current just at the start. So in light of that, let's ask another question. So same exact situation, and all the values are the same for epsilon, R, and C. But now we want to ask the question, what if we wait a really long time after we set the switch to position A? Okay, so it's been charging for a very, very long time. We might as well say, instead of t equals 0, t is equal to infinity. So what is the current going through the resistor and the charge on the capacitor a very, very long time after the switch is thrown? That's the next question. All right, so the previous work that we did, we can still sort of use that. But again, I'd encourage you to pause the video and try to work this out on your own, and then come back to the video once you think you have an answer. Okay, so going back to the document can here. All right, so let's take t equal to infinity. And I just want you to think about how this works intuitively. And you've done a lab on capacitors, charging and discharging capacitors already. So if you recall, current is only going to flow for a short amount of time. Okay? Because current is only flowing as long as it takes to fully charge the capacitor. So once the capacitor is fully charged, then we don't have any current. So I is going to be actually equal to 0 if we wait a really, really long time, because the capacitor is going to be fully charged. And current stops flowing after the capacitor is fully charged. But then what about the Q value, or the amount of charge itself? Well, in this case, let's just go back to the same loop rule equation that we wrote down a second ago. Epsilon minus IR minus Q over C is equal to 0. This time, we're going to set the current equal to 0. So we have epsilon minus 0, and then minus Q over C equals 0. All right, so we have epsilon is equal to Q divided by C, or Q is equal to epsilon times C. In this case, for epsilon, what we have is 10 volts, and for C, what we have is 10 to the minus 10 times 10 to the minus 6 farads, because we have 10 microfarads, and a farad is a coulomb per volt. So what do we have? We've got 100, okay, 10 times 10, 100 times 10 to the minus 6 coulombs, or we can just say 100 microcoulombs. So notice, at the beginning, okay, when there's no charge on the capacitor, it's as if the capacitor is not even there, right? It's as if we just have the battery and the resistor and nothing else. Okay, that's initially what it looks like. And then after a very long time, it's as if the resistor is not even there, and all we have is the battery and the capacitor. Okay, so that's what we've learned so far about what's going on with this RC circuit when we're charging the capacitor. Okay, so the next question I'm going to ask you deals with discharging the capacitor. So same exact situation, and we've had the switch in position A for a very, very long time, which means the capacitor is fully charged. But what we're going to do with this fully charged capacitor is flip the switch to position B, which means now we're discharging the capacitor. Okay? So the question here is, which direction is current flowing while the capacitor is discharging? Is it flowing clockwise or counterclockwise? So I just want to remind you, when we talk about current, we're always talking about conventional current, which means we're assuming positive charge is what's moving around in the circuit. Okay, so let's work this one out. So now what we want to look at, as far as this circuit goes, is the right side, because we've disconnected the battery, which is on the left side, from our circuit. So all that's really happening is we have a capacitor where it's fully charged, so I have plus Q up here on this plate, and then minus Q down here on this plate, connected to a resistor. Just like that. And so the question is, which way is current going to flow? So we're talking about conventional current here. Remember, the direction of conventional current is the direction that positive charges move in the circuit. Okay, so again, we're going to pretend that it's actually positive charges that move around in these wires. And, well, which way would a positive charge want to go if we connect the circuit in this way? Well, I have a bunch of positive charge on the top plate here, and positives tend to attract negatives, and they're going to want to get as close to the negatives as possible. But unless we actually make a path for them to flow, well, they're going to stay separated. But actually, they do have a path to flow. My positive charges are going to want to move this way, up through the wire, through the resistor, and then to the negative plate, where we can just basically neutralize the charge altogether. So this is the direction of our conventional current. That's I. But remember, what's actually happening is electrons are moving the opposite direction. So what's actually happening is electrons on the negative plate move up in this direction counterclockwise onto the positive plate to neutralize the charge here. So the conventional current is going clockwise. Electrons are actually flowing counterclockwise, but again, we're thinking about conventional current here. So I is clockwise. All right. So all of this was kind of a warm-up. Now we're really going to get into the math and the calculus of what's going on here. All right. So what we're going to come up with in this next section is some equations that describe how RC circuits charge. Okay? So let's use that same basic schematic from before, where we have a battery and a resistor and a capacitor here, a second resistor over here. So since we're thinking about the situation of charging the capacitor, we're going to, at t equals 0, set the switch to position A, which allows the capacitor to charge. So there it is. And when we think about the type of current that runs in this circuit, well, remember, current is going to flow off the positive terminal of the battery, and then, if you follow it all the way around, back into the negative terminal of the battery, if we're thinking about conventional current. So in this case, we have a clockwise conventional current, but again, that means electrons are actually going the other way, which is counterclockwise. But let's just stick to conventional current for now. Okay, so we've got that current I, and naturally what that's going to lead to is, well, positive charge building up on the plate that is connected to the positive terminal of the battery, and then negative charge building up on the plate where there's a connection to the negative terminal of the battery. Okay? So we have a current I and a charge Q. But initially, the charge is 0. Okay, so here's what we're going to do. Much like we did in the previous example, we're going to try to analyze what's going on in terms of current and charge in this circuit in terms of Kirchhoff's loop rule. All right, so if we take the loop that's shown here, and we take it in the clockwise direction, so just follow the current, first thing we do is we go across the battery from negative to positive terminal, which means we have a positive epsilon for this voltage. The next thing we do is we go across the resistor in the same direction that the current is flowing, so we have, by Ohm's law, we have minus I times R. And then here we go from the positive to the negative plate of the capacitor, which means we have negative Q divided by C for this voltage. Okay, so these three voltages, when we take the loop and end up back where we started, equals 0. So that's how we apply the loop rule to this RC circuit in the charging case. Okay, so what we're going to do next is a whole lot of math. Okay, so get ready. Big derivation coming up. So I'm going to write down the loop rule equation we just had. It says epsilon minus I times R minus Q divided by C equals 0. And I want to think about this equation real carefully because I have a current I and I have a charge Q, and both of these things are going to be changing, right? I mean, we saw kind of conceptually that the current starts off really high and then it eventually goes to 0, and then the charge starts at 0 and then eventually it reaches some kind of maximum. That's the idea. But I and Q are related. Current and charge are related. If you recall, it's given by this. The current is equal to dq divided by dt. So in other words, we can think of the current as the time rate of change of the charge on the capacitor, which means we don't actually have two different variables, we just have one, which is q. So whenever I see the I in this equation, I'm going to replace it with dq by dt. Remember what I said earlier, this is not just an algebraic equation, this is a differential equation. You see the derivative of q as well as q itself popping up in the same equation. So again, this is more than just algebra, we are going to have to solve this using calculus. Alright, so the next step that I'm going to take is on both sides, let's multiply by c. So I'm going to have an epsilon c right here. I'm going to have minus dq dt rc for my second term. And in my third term, if I multiply c, I'm just going to have minus q. And then the other side's still going to be 0 because c times 0 is still 0. So what I'm going to try to do here, just so you know where this is going, is try to separate out my variables. Okay, epsilon, c, and r, those are all constants. But q is not a constant. And t is also not a constant. So charge and time are my two variables. And what I want to do is separate them out. I want to have all the q stuff on one side of the equation, all the t stuff on another side. So everything I'm going to do for the next couple lines is just all about separating out the variables. All right, so first thing I'm going to do is add the second term to both sides. So I have on the left epsilon c minus q equals positive now dq dt times rc. Okay, so I'm getting close to being able to separate everything else, separate everything out actually, and the way I'm going to do it is by dividing out epsilon c minus q on both sides, multiplying dt on both sides, and then dividing out rc on both sides. So you ready? This is going to be dt over rc on the left, and then dq divided by epsilon c minus q on the right. So there it is. I've separated out time and charge. They're on opposite sides of the equation. So if you see an equation like this, you should be thinking, that kind of looks like what goes inside of an integral. And you'd be exactly right. I can integrate both sides of the equation. And again, as long as I perform the same operation on both sides, it's fine. So on one side, I'm going to have dt over rc, integrate that. And on this side, I'm going to have dq divided by epsilon c minus q, like this. So basically, instead of tiny little infinitesimal changes in time and charge, I'm just going to get the total amount of charge in some amount of time that passes. So in this case, I don't want to just leave this as an indefinite integral. I want to put limits. And what are my limits going to be? Well, on the left-hand side, I have a time. And that can range, well, from 0, that's where we start, to, I don't want to really specify what the top limit is. I just want to call it t. Right? So sometime later, if we start at 0, t is the time after that. So on the other side of the equation, my integration variable is q, so it's an amount of charge. And the limits, well, if t equals 0, q is equal to 0, right? So at the start of this process, there's no charge yet. So I know my bottom limit has to be 0. My top limit is going to be q at time t. So make sure you understand what's going on with the limits here. At time 0, we have no charge. At time t, we have this much charge, q as a function of t. All right, so I have two integrals actually, and I think the easiest way to do this is to look at the integral on each side of the equation separately. So how about we take the left-hand side of the equation first, because that's a really easy integral to do. R and c are both constants, so let's pull those out. 1 over rc, integral 0 to t dt. That's the left-hand side right here. Well, this is a really trivial integral. If you integrate dt from 0 to t, you know what you get? You just get t. So the left-hand side just works out to t divided by rc. That's it. Now the right-hand side, this is going to take a little bit more work. It's not too bad though. Now, there are different approaches to this, but what I like to do for the right-hand side is use a u substitution. Okay? So what we're going to do on the right-hand side is let u equal to epsilon c minus q. And the next thing we have to do is figure out what du is going to be equal to. because not only do we have to substitute out what's in the denominator, but we have to substitute out dq as well. So if I take the derivative of this thing u, well, I have just constant terms in the front, so that's 0. And then this just becomes minus dq. So du is just minus dq by taking a derivative. Okay, we also have to think about the limits, because if I'm changing my variable from q to u, I need to change the limits of integration as well. So my bottom limit was q is equal to 0, but when I plug in 0 for here, in my expression for u, I'm just going to get u is equal to epsilon times c. Okay? And then when my q limit was q at time t, now my u limit is going to be just, again, plug that in, epsilon c minus q at time t. So those are my u limits of integration. All right, so my right-hand side, it looks like this. I'm going to have the integral minus du on top, that negative sign comes in from here, over u on the bottom. Okay, my limits of integration are going to be epsilon c on the bottom, and then epsilon c minus q at time t as my top limit. So for convenience, what I'm going to do is just pull out the negative sign, which means we just have a 1 over u integral, which this is just something you need to remember is the natural log of u. So we have minus ln u going from epsilon c to epsilon c minus q at time t. That's the integral on the right-hand side. All right, so when we evaluate at the limits, we're going to plug in the top limit, which is epsilon c minus q at time t. And then we're going to subtract natural log of epsilon c. Just plug in the top and bottom limits and subtract. That's how this works. And what we have is the natural log of one term minus the natural log of another. If you remember, you can actually combine these two into the same natural log using the division property, where epsilon c minus qt over epsilon c, all in the same natural log, with the negative sign out front, is how this integrates. So that's about as nice of an expression as we can get. And so what we should do is just set the right-hand side equal to the left-hand side. That's all we're really doing here. Okay, so the right-hand side is what we just wrote down. Negative natural log epsilon c minus qt divided by epsilon c. That equals the other side, which we said was t divided by rc. Okay, so the next thing I'm going to do, and maybe without having to write another line, is let's put the negative sign over here. In other words, let's multiply on both sides by -1, because it's going to be convenient to not have it next to my natural log, but instead have it by the t. Okay, so just move the negative sign over, we can do that. And actually now, on the left side, all we have is a pure natural log function. And we want to undo the natural log function because what I'm trying to get out of this is q. I want to know what q as a function of time is. So the way I can start to free that up from the natural log function is to exponentiate both sides. Because when I exponentiate a natural log, I just undo it. All right, so then what we have is epsilon c minus q at time t over epsilon c is equal to e to the minus t over rc. Okay, so if I want to solve for q, here's what I need to do. Multiply on both sides by epsilon c, get rid of it on the bottom here. We have epsilon c minus q at time t equals epsilon c e to the minus t over rc. Okay, I'm solving for q. So let's add it to both sides. Then let's subtract this term with the exponent from both sides, which gives us qt on one side of the equation equals epsilon c minus epsilon c times e to the minus t divided by RC. And we can kind of simplify this by saying here, let's pull out the common factor of epsilon c. And then we'll have 1 minus e to the minus t divided by RC. And we can just kind of take a note on the side here that epsilon c, that's just the maximum charge on the capacitor. Okay? So this is the charge we get after we wait a really, really long time, is epsilon times c. So sometimes we'll just call that Q naught. All right, there's one more thing to do. So this function, just to be clear, it tells you what the charge is at any given time. So you plug in a value of t, and you calculate this, and you get how much charge is on the capacitor. Another thing you might want to know is the current. And so now that we have this Q as a function of time, we can pretty easily get the current because, well, current is just nothing more than dq dt. It's the derivative of the function we just found. So what is the function we just found? Let's pull out, so there's an epsilon c as a constant term. Then we're taking the derivative of 1 minus e to the minus t divided by RC, like this. Okay, so we've got the constant epsilon c out front. If I take the derivative of the first term, that's just the derivative of 1 with respect to time, but that's a constant, so that's not changing. My second term already has a negative sign there, so let's keep that straight. And I'm taking the derivative of an exponential function, but it's not a pure exponential function. I actually have to use the chain rule and take the derivative of what's inside. Okay, so what's the derivative of what's inside? I've got minus t over RC. Well, if I take the derivative of this with respect to time, I'm just going to get minus 1 over RC, because the derivative of t goes to 1, and then we have these constants. And then, the way derivatives for exponentials work is you just have the same exponential function as before, minus t over RC. Okay. All right, so let's kind of consolidate everything we have here. So first, we just have two negatives, so that's positive. We have a c on top and a c on the bottom, which cancel. Overall, we have epsilon divided by r times e to the minus t over RC. So this is the current as a function of time, whereas this is the charge as a function of time for a charging RC circuit. And this right here, we can call this I naught, epsilon divided by r. This is the maximum current that we get. Okay, so this is the maximum current. All right, so that was a lot. Let's summarize everything we just did. We have Kirchhoff's loop rule, and that looks pretty simple on its face, but when you realize it's a differential equation, there's actually a lot that goes into solving that. And what we got were our two RC circuit charging equations. So what does this say? The current as a function of time is equal to I naught, which is your maximum current, times e to the minus t divided by RC. Your charge on the capacitor as a function of time is Q naught, which is the maximum charge, times 1 minus e to the minus t over RC, just like this. And just to recall what we just said, the values for I naught and Q naught are as follows. Maximum current, epsilon over r. Maximum charge, epsilon times c. Okay. So let's get some kind of handle on what these functions actually look like. And let's plot them out. So let's start with the current equation, because that's a little bit simpler to look at. all this function is telling us is we have some kind of maximum current at the start of the charging process, and then it just exponentially decays after that. So the current is exponentially getting smaller and smaller and smaller. That's what a negative exponential looks like when you plot it out. Okay? But in the exponent, we keep seeing this factor of RC, and it looks like there's something important about R times C as it appears in this equation and appears in this equation. So we're going to get into that in a second, but let's plot out our charge equation. What does this look like? Well, since instead of a pure exponential decay, it's 1 minus that exponential decay, this actually has a different shape to it. So we start at 0, and then the charge ramps up. We're getting more and more charge on the capacitor, and then it basically flattens out at some point where we reach our maximum charge. Just like the current, basically, at some point is going towards 0. Okay? But what I want to show you next is the number R times C that appears in these equations is telling you how quickly the charging is happening. Like how fast does it charge up? Does it do it really quickly or really slowly? RC has something to do with that. Okay. So to give you a sense of what I'm talking about, let's just do a little bit of math using exponents. My charge at time t is equal to Q naught times 1 minus e to the minus t divided by RC. That's just my, my charge on the capacitor as a function of time. So here, let's try something. Let's plug into the equation a time which is equal to R times C. What happens? Well, we get Q naught, and we get 1 minus e to the minus t, but I'm plugging in RC for the time. So now I'm going to have RC divided by RC. So to simplify, this is just Q naught, and then 1 minus e to the minus 1. Okay, so this is a number. You can actually calculate 1 minus e to the minus 1. So punch that into your calculator, and you're going to see that this is 0.63 Q naught. Okay, what if we plug in a time that's equal to 2 times RC? What happens then? Well, basically, instead of e to the minus 1 here, you're going to have e to the minus 2. So you have Q naught times 1 minus e to the minus 2. Again, calculate that number. Punch 1 minus e to the minus 2 in your calculator, and what you'll see is, what pops out is 0.86 times Q naught. Okay? Let's do it for 3 times RC. It's going to be Q naught times 1 minus e to the minus 3. What's that going to give you if you crunch this number is 0.95 Q naught. So this RC thing is telling us something about how long it takes to charge up. Because if we have 1 times RC as our time, it's like 63% to a full charge. If we have 2 times RC, it's 86% of the way to a full charge. And if we have 3 times RC, it's like 95% of the way to a full charge. Okay, so it's telling us something about how quickly the charging is happening. Now let's do the same thing with current. Current as a function of time is I naught e to the minus t over RC. And so what does this look like when we plot, or when we plug in RC for the time? Well, here, let's see. We have I naught, and then if I plug in RC for the time, I just get e to the minus 1. And that's actually 0.37 I naught. Okay, what if I plug in 2 times RC? Well, that's going to be my I naught, that's the maximum current. E to the minus 2. So again, just punch that into your calculator, do e to the minus 2. You're going to get 0.14 I naught. And then do it for 3. And of course we could just keep going forever, but let's just stop here. If I have 3 times RC for my time, I get I naught times e to the minus 3. And what is this? This is going to be 0.05. So let's think about this. After this much time passes, RC, I've dropped to 37% of the maximum current. If I do 2 times RC, if I wait this long, now my current is even less. It's only 14% of its peak at the beginning. If I wait 3 times RC, then it's only 5% of that maximum current. Okay, so what's happening? The charge is getting bigger over time, the current is getting smaller over time, and RC, that quantity, has something to do with how long it takes. Okay? So that's where I came up with all of these different labels on the plots. That's how I know, again, that RC is the time we get 0.63 Q naught, 2RC we get 0.86 Q naught, and so on. That's where the labels came from, just working out that math. Okay, so the next thing we need to go over is something called the time constant of an RC circuit. And first, let's just give the definition. So the time constant is given by this Greek letter tau, and it's just the product of the resistance and the capacitance. So it's R times C. Now, that product of R and C is appearing all over the place in our equations so far. So for instance, if we look at the charging equations that we just derived, the charge as a function of time is Q naught times 1 minus e to the minus t over tau. So the tau appears in the exponent, just like it does for the current equation. And so basically what the time constant is telling us is how quickly is the capacitor able to charge and discharge. Okay? Now it's not obvious that a resistance value times a capacitance value is going to give you a time. So let's think about why that would be the case. Well, a resistance value in the SI system is going to be given in ohms. And capacitance is going to be given in farads. So if we remember the unit equivalencies here, an ohm is a volt per amp, and a farad is a coulomb per volt. So just make those substitutions right here. Okay, the volts cancel. Now we have a coulomb per amp as our unit. Well, an amp is nothing more than a coulomb per second, because that is a unit of electric current. Okay? So it's a coulomb per second in the SI system. And then when we cancel out coulombs, and then the seconds actually go to the top, we realize that it's equal to 1 second. So an ohm times a farad is equal to a second, so yes, this is some kind of time. And it makes sense that the time constant should be given by R times C. Okay, so the bigger the value of resistance, let's say, okay, the more resistance to current flowing in the circuit there's going to be. And that means it's just going to take longer to either charge or discharge the capacitor because current is flowing more slowly. Okay, so R increases tau. That should be kind of intuitive, right? Because the more resistance we have, the slower the charge is going to move, the more time it's going to take to charge or discharge the capacitor. Now, on the other hand, why does C come into the equation? Well, remember, capacitance is really just a measure of the device's ability to store charge. So the higher the C value, the more charge it's going to store. So if it's storing more charge, then the longer it's going to take to actually charge or discharge the circuit, because you just need to get more charge on the capacitor, right? So again, it makes sense that as C goes up, so does tau. All right, so that's the intuition for the time constant. So the next thing we have is an example problem. And in this example problem, what we're doing is we're charging an RC circuit where the resistance value is 10 kilo ohms and the capacitance value is 10 microfarads. So we have a couple questions about this. First, what is the time constant? And then how long is it going to take for the current to fall to 50% of its maximum value? And then how long is it going to take for the current to fall to 0.01% of its maximum value? So remember what the current is doing. The current is exponentially decaying. So let's work it out. So in this case, the time constant Just use tau is equal to R times C. That's all we need to know. So the resistance value is 10 kiloohms, or 10 times 10 to the 3 ohms. 10 to the 3 is the kilo prefix. And then the capacitance is 10 times 10 to the minus 6 farads. It's the same as 10 microfarads. And again, we just showed that an ohm times a farad is a second. So written this way, it's going to be a time measured in seconds. So you do the calculation, and it's a nice round number, 0.1 seconds. So it's a tenth of a second for your time constant. Okay, so let's answer the next question, which is how long to reach 50% of the maximum current, which we call the maximum current I naught. Okay, so I'm looking for a time here. And the way we're going to figure out what the time is to use our equation. Okay, the current as a function of time is equal to I naught times e to the minus t divided by tau. That's how the current exponentially decays in this circuit. So I'm looking to solve for t, so without plugging in any numbers yet, why don't we just rearrange the equation to solve for t. And the first thing we'll do is divide out the I naught. So I have I over t, or I as a function of time, divided by I naught, is equal to e to the minus t divided by tau. So if I'm looking to solve for t, what I should do next is take the natural log of both sides. So I'll have ln, I as a function of time divided by I naught, equals, when I take the natural log of an exponent, I just get rid of the exponent. So I just get minus t over tau. So what do we have? T is equal to negative tau, natural log of the current at time t, divided by the max current. Okay, so in this case, what are we going to actually plug in for the current? Well, we're going to plug in 50% of I naught, or in other words, as a fraction, not a percentage, this is a half, or 0.5 of I naught. So then the time ends up being minus 0.1 seconds for tau, natural log of 0.5 times I naught over I naught, so we're just going to cancel those out. So it's 0.1 times the natural log of 0.5 with a negative sign in the front. Okay, so crunch those numbers. You should be getting 0.069 seconds. And technically we would keep, I guess, one sig fig here, so let's just say 0.07 seconds. Okay. The next follow-up to this is a very similar sort of question. How long to reach 0.01% of I naught? So we can use the same exact expression we just developed over here, as t is minus tau, natural log, I as a function of time divided by I naught. And in this case, what are we going to put in for the current at time t? We're going to put in, well, if this is a percentage, to make this a fraction, right, some factor times I naught, we'll have to divide by 100, just like, 50% is 0.5, 0.01% is actually 0.0001 times I naught. So, plug in the numbers. We've got minus 0.1 seconds, that's tau, natural log, 0.0001 I naught, divided by I naught, so of course, whatever that max current value actually is, it doesn't matter, it just drops out. So to calculate, we're going to do minus 0.1 times the natural log of 0.0001. And this works out to 0.92 seconds. 0.9 seconds, I guess, if you want to round to 1 sig fig. And so of course it takes much more time to reach this small of a current compared to just 50% of maximum, right? The current is exponentially decaying, so to reach this tiny of a current value, it's going to take much more time. That's the idea. Okay, so moving on. We've developed the equations that describe an RC circuit in the process of charging. Now what we're going to do is figure out what the equations are for discharging. Okay? So we're using the same basic circuit that we used before when we developed the charging equations. And there's a switch that can be set to either position A or position B. So we're going to imagine that the switch has been in position A for a very long time, so it's already charged the capacitor. Okay, but what we're going to do next is actually disconnect this charged up capacitor from the battery by throwing the switch to position B. Okay, so now we're going to put the switch over here, and we're going to be in a situation where the capacitor is discharging. It's losing its charge. So now the switch is in position B. And notice how the battery is not even part of the circuit anymore. It's disconnected. And basically all that's happening is we can have current flowing in this loop right here, but there's nothing that can happen in the side that's disconnected. And how does current flow? What direction does it flow in? Well, think about it this way. If we have positive charge on the top plate, and conventional current is all about how positive charge moves, well, positive charge is going to want to move off this plate, loop back around to the negative plate, so it can just neutralize. Now, in reality, of course, what's really happening is electrons are moving from the negative plate onto the top plate to neutralize that, but again, this is conventional current. So the conventional current is actually clockwise. Okay, the electrons are flowing counterclockwise in reality. So let's do a quick Kirchhoff's loop rule equation given this circuit. So what do we have? We have two terms to add together to give us 0 in the loop rule. If we take our loop to be going clockwise like this, maybe we can start over here. We're going to go across the capacitor plates from negative to positive. All right, so if we go from negative to positive, we have a positive voltage, which is Q over C. And then after that, we have to go across the resistor in the direction that current is flowing. So the voltage is minus I times R in that case. And that's our loop rule equation. That equals 0. So the next thing we'll do is use that loop rule equation to figure out Q and I as a function of time. Okay, so our loop rule equation says minus I times R plus Q divided by C equals 0. And again, this looks deceptively simple, but it's actually a differential equation because I is related to Q in terms of a derivative. Okay, so let's write that down. So before, when we did the derivation for a charging circuit, we said I is dq dt, and that was fine because the more and more charge that builds up, or the faster charge builds up on the plates, the more current we have. But in this case, there's a negative sign, which means, okay, why is that negative sign there? The negative sign is there okay, the negative sign is there because the charge decreases as the current flows. Okay. So a decrease in charge gives us a positive current. They're related by a negative sign here. So let's sub in minus dq dt in for current. And so we have minus negative dq dt times R plus Q over C equals 0 in the loop rule equation. So we can simplify that. First thing is we have two negatives, just drop those out. We also have a factor of c in the denominator here. I'd like to just multiply that all across the board. So we'll have rc plus q equals 0. So just multiplying through by c gives us this. All right, the strategy from here on out is pretty similar to what we did before, where we're trying to separate out the variables of q and t. So we want the charge and the time to be separated out. So what I'll do is I'll take q is equal to minus dq dt times rc. So I just subtracted this from both sides. And the next thing I'm going to do is a little bit of cross multiplication. I'll multiply on both sides by dt. I'll divide on both sides by minus rc. And then I'll divide on both sides by q. So what does that give us? Well, we're going to have, on one side, we'll have minus dt over rc. And on the other side, we'll have dq over q. So that's just a simple rearrangement of what's happening here. And as usual, when you look at an equation like this, you should be thinking, I can integrate both sides. So I have minus dt over rc equals dq over q. And I want to make these definite integrals. I want to put the limits of integration on each one. So how about we start with the time? For our time integral, we have this going from 0, okay, because that's when we start the time, to t, just sometime later. Okay, for charge, what's the bottom limit going to be? It's not going to be 0. We don't actually start off with 0 charge because in this case, we start off with the maximum amount of charge. We start off with q naught. Then later, we have some new charge, q at time t. Think of it this way. Okay, so at time 0, we have our maximum charge. Sometime later, we have some different charge. That's what this is saying. All right, so let's evaluate the integrals. On the left-hand side, well, all we really have is, if we pull out some constant factors, minus rc, integral from 0 to t, dt. Well, this just integrates to t, so we're going to have minus t over rc. That's the left-hand side. The right-hand side, it's actually not that bad, because we don't need to do any sort of u substitution. We know exactly what this integrates to, because 1 over q integrates to the natural log, ln q. And we have to evaluate between the limits of q naught and q at time t. So we have natural log, top limit is q at time t, bottom limit is q naught. And then once again, we're going to use the property of logs, called the division property, where we can bring these two terms into the same natural log by division. So this is natural log of q at time t divided by q naught. That's the right-hand side. So we evaluated the two integrals separately, but we have to set the left-hand side equal to the right-hand side. That's how this works. So what do we have on the left-hand side? Minus t over rc. On the right-hand side, natural log qt over q naught. What I'm trying to figure out here is q at time t, which means I need to get it out of the natural log function. So just like before, we're going to exponentiate both sides, which gets rid of the natural log here and then gives us an exponential decay on the other side. So I have e to the minus t over rc equals qt divided by q naught, which means q at time t equals q naught e to the minus t over rc. So what is this saying? This is saying the charge on the capacitor is exponentially decaying. It's not increasing with time because we're discharging it. It's exponentially decaying. It's going away. All right, the next thing is current. So the current is given by minus dq dt, as we said just a second ago. And we have q as a function of time, so we can just take the derivative of that. I have a negative sign out front. I have a q naught constant factor. Might as well pull that out. And then I have d dt of e to the minus t over rc. So it's the derivative of an exponential, but we also have to use the chain rule because I don't just have t in the exponent. I have this factor of minus 1 over rc. That has to come out. So here we have minus q naught, factor of minus 1 over rc from the chain rule, and then e to the minus t over rc. That's how we take the derivative of this thing. And of course, that gives us the current. But remember, from before, when we see q naught, we're talking about the maximum charge, which is epsilon times c. So cancel out the two negatives. On top, we have epsilon times c. On the bottom, we have rc. E to the minus t over rc. Cancel out the c factors. What do we have? Epsilon over r, e to the minus t over rc. And then just remember that this is our maximum current. The maximum current is epsilon over r. So actually the equation here, let's check each one we derived. When we're discharging, the equation for the amount of charge on the capacitor is different from before, but the equation for current has the same form. It's exponentially decaying. So we started with Kirchhoff's loop rule. We solved the resulting differential equation, and this is what we got. Both I and Q are describing an exponential decay. Okay, so this is what we use in the case of a discharging RC circuit. Okay, so the next thing is plot these functions out. So since they're both basically exponential decay functions, they look the same in terms of their shape. And we already worked out from before the fact that if we wait one time constant, RC, that the current is going to fall to 37% of its starting value. The same is true for the charge. So after one time constant, the charge is 37% of its starting value. And similarly, after two time constants, 2 times RC, everything has fallen to 14% of the starting value, and 5% of the starting value after 3 time constants. Okay, so we have these two exponential decay functions, and that's what they look like. Okay. So with that said, we're going to move on to an example. So we're going to consider the circuit shown here, where epsilon is equal to 18 volts, C is equal to 4 microfarads, R1 is equal to 5 times 10 to the 5 ohms, R2 is equal to 3 times 10 to the 5 ohms, and initially what we have is the capacitor uncharged, so there's no charge on it, and the switch is open. Okay? So just like shown here, this is what we start with. The switch being open, capacitor being uncharged. But what we're going to do is close the switch, and what that allows the circuit to do is connect the battery to the capacitor, and that will charge up the capacitor, right? So what we're going to do is find the current through this resistor, R1, after 1.5 seconds. So it's charging up. After 1.5 seconds, how much current do we have? All right, so then what we do is we wait a really long time until the capacitor is fully charged and current stops flowing in this branch of the circuit. And when it's fully charged, we'll open the switch again. So what happens when we have a charged capacitor and we're opening the switch again. Well, now what's happening is the capacitor is discharging. Okay? So as it's discharging, we're going to find the current after 1.5 seconds after the switch is reopened. Okay? So that's the problem. And to solve it, we'll do it on paper. So here, let's first look at the case where the switch is initially closed. And let's kind of sketch out the circuit to see what it looks like when we initially close the switch. So here's the capacitor. Here's the first resistor, R1. And then in this middle branch of the circuit, that's R2. And then that's all connected to a battery, which is over here on the right branch. Okay, so let's label that as C, R1, R2, and epsilon. So for the battery, let's note where the positive and negative terminals are. So as soon as we connect to the battery, we expect that the top plate of our capacitor is going to have some positive charge on it, whereas the bottom plate is going to have some negative charge. And that means some current is flowing in this branch of the circuit. Let's call this I. How do I know the current is flowing this way? Well, remember, conventional current is telling you which way positive charge is moving. So if the top plate is acquiring a positive charge, then the current should be going towards the top plate. So that's why. All right, so what we're going to do next is kind of carefully analyze the circuit using the loop rule. And in this case, let's do the outer loop. And how about we take it counterclockwise this time? Okay, so I really want to just take a closer look at what's going on in the circuit before we just jump to one of our equations. Because the reason is, which R value am I going to use? Am I going to use both of them or just one of them? I better analyze the circuit a little bit more carefully before I jump to any conclusions. So if we're doing the loop rule, counterclockwise on the outer loop, let's start here. We go across the battery, which means we have a positive epsilon. The next thing we do is we're over here, going across the resistor in the direction of current. So we have minus I R1. Then the next thing that happens is we go across the capacitor from the positive plate to the negative plate, which means we have a minus Q over C term. That equals 0. How does the current here relate to the charge on the plates? Well, this current is really just giving me the time rate of change of the charge on these plates. It's just dq dt. So, okay, at this point, we don't need to go much further. This is an RC circuit charging, okay, where we just use the C value here, but we use R1, okay? Because what's happening? This circuit, okay, or the capacitor is charging through resistor number 1. R2 doesn't actually come into play here. Okay, so RC circuit, we're charging through R1. And now we can just jump to the equation because I know that, well, the current as a function of time is given by epsilon divided by R, e to the minus t over RC. And now I know that the relevant R value is R1. Okay, so that's why we did this analysis first. Like, we know which R value to use. So this is just a plug and chug at this point. We'll take the time to be equal to 1.5 seconds, and we want to know what the current is at that time. So we have 18 volts, divide out R1, which is 10 to the 5 volts per amp, or ohms. And then we have e to the minus, the time is 1.5 seconds, and then we'll divide out 5.00, 10 to the 5, that's my R value, R1, ohms, and then C, in this case, was 4 microfarads, 4 times 10 to the minus 6 farads. And just to take note of the units here, remember an ohm times a farad equals a second. So we don't have any units up in the exponent, which should be the case. And okay, so just crunch the numbers, and here's what you get. 1.70, 10 to the minus 5 amps. So that's the current after 1.5 seconds. Okay, so close the switch, 1.5 seconds later, that's the current running through this resistor. That's what we found. The follow-up question to this was, okay, if we wait a really long time, so now the capacitor is basically fully charged and this current is basically gone, now we're going to reopen the switch. So we have to think carefully about what the circuit looks like when we reopen the switch. Because the switch, if you recall, is right up here. Okay? And if I open it, I'm basically disconnecting everything on the left side from the battery. Okay, so all that's happening at that point is the only place that we can have any current flowing is in this leftmost loop of the circuit. So here, let's just draw that part of it. So that's all that matters at this point. Okay, so we have the capacitor, we have R1, and we have R2. And we start off with a fully charged capacitor with plus Q and minus Q on the top and bottom plates respectively. And how's current going to move around in this circuit? Well, as we said earlier, it's going to want to come off the positive plate and then flow around like this and neutralize the negative plate. That's the conventional current. So here, this is when we reopen the switch. That's what I'm showing down here, is the reopened switch. Okay, so again, we want to do a little bit of analysis on the circuit using the loop rule, just so we can understand which R values are going to be used here. Okay, and as it turns out, and hopefully you can just see it here, the current is going through both resistors, so the charge is actually, or the capacitor is discharging through both of these two resistors. All right, but the loop rule looks like this. Here, how about we go clockwise, start down here, go from the negative to the positive plate of the capacitor. So that will be a positive Q divided by C. And then go across resistor number 1 in the direction of the current. Okay, go across resistor number 2 in the direction of the current, so that's minus I R1 and then minus I R2. Same current, just one continuous loop, equals 0. Okay, so actually you can join these two resistance terms together. We have Q divided by C minus I times R1 plus R2 equals 0. So basically what's happening is you have these two resistors in series now, and effectively it's like you just have one resistor with the combined resistance R1 and R2. Or we can think of this as the equivalent resistance for two resistors in series, like these two are currently organized. So here, R1 is 5 times 10 to the 5 ohms. R2 is 3 times 10 to the 5 ohms. So when we add them together, we get 8 times 10 to the 5 ohms. Okay? So that's the resistance we should be using in our equations, because it's discharging through the series combination of R1 and R2. Okay? So with that said, we have the RC circuit, and we're discharging through Req. So now let's think about what kind of current do we have, or what's the formula for the current as a function of time. It's, well, same as before, epsilon over R. And then we have e to the minus t over RC. But now we know the R value we should be using is Req. Now it's a plug and chug problem because the time is 1.5 seconds. The epsilon, as before, is 18 volts. Divide out 5, 10 to the 5 volts per amp. And then we'll take e to the minus 1.5 seconds, divide out 8.00, 10 to the 5, or I'm sorry, just to go back to here, Req is supposed to be 8 times 10 to the 5. Okay, and then it's 8 times 10 to the 5 up. And the exponent times 4 times 10 to the minus 6 for the capacitance. All right, so crunch these numbers, and what you get is 1.41, 10 to the minus 5 amps. Okay? So the takeaway of this problem is, we can use these equations we derived from before, but every circuit is a little different. So you have to be really careful about, okay, what is the resistor I'm charging through? What is the resistor or set of resistors I'm discharging through? So you'll have to do a little bit of work sometimes to figure out how to apply these equations. It's not always so straightforward. All right? And just as another note, you should be able to derive all of the charging and discharging equations as we've worked them out in this lecture. Okay, that's something you should know how to do. All right, so that was the first example. And what we're going to do is one more example. And this is kind of a long one. And after this, the lecture will be over. So there are practice problems at the end of this lecture, just like every other lecture. I don't think we're going to have time to do any in this video, but keep in mind the practice problems are just on the Canvas slides that you have available to you. And my handwritten notes are going to be available too if you want to see any solutions to those practice problems, but we'll just end the video after this one. Okay, so the example here is backup power. And I think the first time we ever talked about capacitors, I did mention that one use of capacitors is a backup power source. So in other words, let's say you're connecting some kind of device, like a computer or something like that, to a wall outlet, and the power goes out, just out of nowhere. All right? You can use a capacitor as a backup source because that can deliver charge or deliver current to your device even when your main power source has gone out. And that's pretty much what's happening in this example, right? So we have a device with a load resistance, big R is 45 ohms, connected to a 240 volt DC power source. So that's over here. Okay, so this is 240 volts. You can imagine this is a battery or something like that. There's a capacitor which is connected in the circuit like this, which is going to serve as our backup power source in case this main power source fails. Okay, so the device here, we're given some specifics about it. It's going to stop working properly if the current falls below 3 amps. So in other words, if the current is above 3 amps, it works just fine, but if the current gets too small and it falls below 3 amps, it's just not going to function properly. So we always need the current to be at least 3 amps to make it work properly. As far as what this device actually is, it can really be anything. It could be, a light bulb, it could be an electric motor, just something that has a resistance of 45 ohms. Okay, so at t equals 0, the main power source is disconnected. Okay, so literally, just imagine taking this out of the circuit and it's disconnected. So what's going to happen? The capacitor is now our backup power source, and it's going to begin to supply current to our device. Okay, because initially the capacitor was charged up, then we knocked out the main power source, and what happens when you just have a capacitor connected to a resistor and nothing else in the circuit? Well, the capacitor discharges. So when the capacitor discharges, it's giving current to the device, and that can keep it running for a limited amount of time. But of course, the current gets smaller and smaller as time goes on. It's actually an exponentially decaying current, as we found previously. So it's only going to last so long as a backup source before the current gets below 3 amps. So the question is, how long is it going to take for the current to go below 3 amps and for the device to stop working correctly? And the second question here is, how much energy is used by the device in this time? Okay, so let's go through that. And there are a few things we just want to sort of jot down and have in our heads. So, when the power source, I should say the main power source, is connected, the capacitor is fully charged. And we don't know how much charge it's holding necessarily, but we do know it's charged to a certain voltage, which is 240. Okay, now let's imagine the main power source being disconnected. And how that affects our circuit. So basically, the left branch of the circuit with the power source, that's gone. All that's left is we've got the capacitor and the device. There's nothing else. And it's a pretty good capacitor, right? It's 1.5 farads, so it's storing a lot of charge. So initially, when the power source is disconnected, and again, this is going to be at t equals 0, we have some charge on the plates, plus Q and minus Q on the top and bottom, respectively, and a resistor over here. All right, so this is clearly a discharging capacitor. Again, what the capacitor, or what the positive charges on the top plate are going to want to do is move around the circuit until they get to the bottom plate to neutralize it. So that's the direction current is going to flow. So conventional current going clockwise. And let's just write down the loop rule equation. Let's say we go clockwise when we take the loop. So this is pretty easy, just one single loop. If we go across the capacitor going clockwise, we're going to have a voltage increase because I'm going from negative to positive. But then I have a voltage decrease when I go across the resistor because I'm going in the direction of current. So I have minus I times R. That's the whole loop, so that's 0. Okay, at this point, we don't have to do too much more. We know that this is just an RC circuit discharging. And it's pretty obvious that this is our R and that's our C value in this case. So we can just jump right to the current as a function of time is epsilon over R times e to the minus t over RC. So that's how current is changing as a function of time. So remember, ideally this device is just getting some kind of constant current, but what it's getting from the capacitor is an exponentially decaying current. So it's only going to work for a short amount of time before the current is just too small. So what we want to find is, how long will it take for I to get to 3 amps? So we basically want a time. Okay, well, I can plug in 3 amps for the current. That's on the left side, right here. On the right side, epsilon is 240 volts, and the resistance is 45 ohms, which is volts per amp. And then I have e to the minus t divided by R times C. So we have, what do we have? R is 45 again. And then C is 1.5 ohms in farads. Again, that gives you a second as the time. All right, so let's do a couple things. We're trying to figure out T. So let's multiply by 45, divide by 240 on both sides of the equation. And then we have e to the minus t. Now here, R times C is 67.5. Is that right? Yeah, 67.5. And that would be units of seconds. Okay, so I'm trying to find t, which means I need to get it out of the exponent, which means we're going to natural log both sides. Okay, and the left side, if you crunch these numbers, is 0.5625. So the natural log of 0.5625 is equal to minus t over 67.5 seconds. So guess what? The time I'm looking for is going to be minus 67.5 seconds, and multiply that by natural log 0.5625 to get, this actually works out to 38.84 seconds, but we'd round that to 3 sig figs, so 38.8 seconds. So that's how long you have for this capacitor to actually work as a good backup power source, but after that, it's not going to work. So let's say this is your computer. That's how long you have to save all your files and shut it down. 38.8 seconds. Okay, so that's the time. There's a second question, and the second question asks about how much energy is used by this device in this time. Okay, so from the moment our main power source fails until our backup power source fails, which is 38.8 seconds, how much energy is the device using? Well, there are kind of two ways to think about this. And the first way is the energy that is used by the device is coming from somewhere. Well, it's coming from the capacitor, right? So the capacitor stores energy. The more charge it has, the more energy it stores. And if it's losing charge, it's losing energy and it's giving it to the device. That's the idea. So the energy used by the device is coming from the capacitor. And we can write that as an equation. The energy used by the device is equal to minus delta U capacitor. The negative sign just means as the capacitor loses energy, the device is using the energy. Okay, so that's what the negative sign is for. And then this is a throwback to chapter 24, but the energy stored in a capacitor, we derived this, is Q squared divided by 2C. Which means the energy used by our device is minus, this is a delta, so think of it as a final value, Q final over 2C, minus an initial value, Q initial squared over 2C. Yeah, I should have said squared, right? All right, so we can write this in a slightly simpler way. I have a common factor of 1 over 2C. And then if I distribute the negative sign into the brackets, it just flips the order of the terms. So we have Q initial squared minus Q final squared. Okay? So 1 over 2c, Q initial squared minus Q final squared. So basically, how much energy is being used by the device is just directly related to how much charge the capacitor is losing. Okay, and what is the equation that describes how a discharging capacitor is losing charge over time? It's this. Okay, Q as a function of time is given by epsilon c, e to the minus t over RC. Remember, this is for the discharging case. That's what we're dealing with. And epsilon c is just another way of saying this is Q naught. Okay? But in this case, I want to think of it as epsilon times c. All right, so here's what we do next. We calculate our initial and final Q values. So Q initial, what's that equal to? Well, that would be the charge on our capacitor at t equals 0. Okay, so I'm going to take epsilon times c, and then I'm going to plug in 0 for the time, so I'm going to have e to the 0 power. Well, e to the 0 power is just 1. So you have epsilon times c, and that's it. So the initial charge is 240 volts times 1.5 farads, which is coulombs per volt. And this gives you 360 coulombs. That's the initial charge. That's actually quite a bit. The final charge, well, okay, we're going to have epsilon c, which we just calculated, that's 360 coulombs, times e to the minus, what do we put in for the time? Well, the time over here is 38.84 seconds. And then RC is 67.5 seconds, as we found previously, so let's just put that in. Okay, so that's what it looks like when we plug the numbers in at t equals 38.8 seconds. Sorry, I meant to put that in there. And numerically, this comes out to 202.49 coulombs. So that's the final charge. Meaning, the energy used by the device, we can now just calculate directly. It's 1 divided by 2 times c. C is 1.5 farads. And then we've got 360 coulombs. That's our Q initial squared. Minus 202.49 coulombs. Square that. And it turns out to be a pretty substantial amount of energy. It's 2.953, 10 to the 4th power joules. We'd round that to 2.95, 10 to the 4. That's how much energy we're using while the backup power source is functioning. Okay, there's actually another way to do this. And the way we do this, let's call this our alternate solution to the second question. It's to think about power. Okay, so the power for the device is I squared times R. And we know exactly what I is equal to, right? The current running through the device, we just said a second ago, is equal to epsilon divided by R, e to the minus t over RC. So what I can do with that is find power as a function of time by plugging in this for the current. So plug in that expression for the current and square it, and then multiply by R. That will be your power as a function of time. Okay, so let's simplify that. We have an epsilon squared on top because we square the term in brackets. We have an R squared on the bottom, but we cancel with one factor of R over here. And then, so yeah, the constant factors are epsilon squared over R. Then we have this exponent, Now, remember, when you square an exponential, the 2 just goes into the exponent as a factor. So you have minus 2t over RC. That's how you deal with the square. And so this is the power as a function of time. What it's telling you is the power is also exponentially decaying. So it's using energy at a slower and slower rate as time goes on, as the current dies out. Now, when we talk about the power of the device, we're really talking about the energy consumed per unit of time. Or we can think of it as a derivative of energy with respect to time. And in this case, we can write dE as P times dt. Just rearranging the definition of power tells us that dE, some kind of infinitesimal amount of energy being used by the device, is the power of the device times some infinitesimal amount of time, dt. And so, what we can do is plug in the power wait, hold on a second, guys. I wrote something wrong up here. On the bottom, that should be RC, of course. Okay. So in the exponent, it's minus 2t over RC. And then there's the dt. Okay. So what we want is to integrate both sides, because I want the total amount of energy used by the device, not just some infinitesimal amount in a tiny amount of time. So I'm going to integrate the left side, which is dE, which means I'm going to also have to integrate the right side, pull out the constant of epsilon squared over r, and then we'll integrate e to the minus 2t over rc dt. Now let's think about limits of integration on this thing. As far as time is concerned, we're going from 0, which is when our main power source fails, all the way out to t, so we can just plug in any value of t when the time comes. Okay, for the energy, well, 0 energy is used if no time has passed, but then at the top limit we'll have E, the energy used at time t. Alright, so we've got two integrals, and the one on the left side is pretty simple. You know, when you integrate dE, you just get E, and then we have to evaluate at the top limit, which is E at time t, minus the bottom limit, which is 0. And then over here on this side, let's figure out the integral. Well, it's epsilon squared over r. How does this function integrate? It's an exponential, but we have to actually account for the factors inside the exponent. So if it was just e to the t, that would integrate to e to the t. But since we have these extra factors, here's how it integrates. We have minus rc over 2 times e to the minus 2t over rc. So you have to, in other words, you have to take the inverse of the constants in the exponent to get the integral. So cancel out r. And actually, we have to be careful here too, because we're not just done at this point. We have to evaluate at the two limits. Well, you might be saying, okay, well, I just plug in t, and that doesn't change anything. And then I plug in 0, and we actually don't get 0 when you plug in the bottom limit. That's what we have to account for. So, okay, on the left side, I just have energy used at time t. Then I have epsilon squared c over 2. And then that's what the simplified factors are. Oh, I have a negative sign out there too, right, because there's a negative sign there. So plug in the top limit, we get e to the minus 2t over rc. Now plug in the bottom limit and you get e to the 0, which is actually 1. E to the 0 is 1. Okay, so that means the energy used at time t is this. let's take this negative sign out front and put it into the brackets, which means we're going to flip the order of the terms. The first one is e to the 0 now, which is 1. And then we have minus e to the minus 2t over rc like this. And, okay, now I can just plug in the numbers, because by thinking about this in terms of power, I was able to come up with an expression for how much energy is used after a given amount of time has passed. Okay, so now what we're going to do is plug in the time of 38.8 seconds and just see what comes out. So we'll have 240 volts, and we'll square it, multiply by 1.5 farads, divide by 2, and then take 1 minus e to the minus 2 times t, which is 38.8 seconds, and then divide by rc, which we said was 67.5 seconds. Okay. So take a second to calculate this. And what you should be coming up with is 2.953, 10 to the 4 joules, round to 3 sig figs, 2.95, 10 to the 4. Check it out, it's the exact same answer we got up here. So the two ways to think about how much energy the device uses is, well, in terms of power, but power is a derivative of energy, so you have to do a little integral to actually get the energy. Another way, maybe this is a little more straightforward for people, is to think about the fact that the energy is coming from the capacitor. So whatever energy the capacitor loses, the device gains. So the interesting thing is, however you think about it, it works out the same way. All right. So that's it for the RC circuits portion of this lecture, and that's it for chapter 26, because that was the last topic. And the next time you see a lecture video, we're going to be on chapter 27, which has to do with magnetism. We're going to introduce magnetism in that chapter. Again, the practice problems are available at the end of the lecture slides, so feel free to do those for extra practice. And then just be safe, be healthy out there. I'll see you in the next video.